Good evening, teacher. We're going to talk about Cohen, Coon, Tunning, synchronization. Next one. The Cohen Coon is a classical technique designed to calculate PID controller parameters based on the stepped response of a first-order plus dead time FOPDT system. It accounts for processes dead time theta and a time constant tau to provide a balance between fast response and system stability, making it effective for processes with significant delays. By using predefined formulas, it provides a systematic way to tune PID controllers for achieving desired performance in terms of minimizing overshoot, setting time, and steady-state error. Next one. And it also has some advantage and disadvantage as well. For advantage, we've got that it's a quick tuning that provides an structure and a fast method to estimate PID parameters. It also performance oriented. It has a balanced overshoot, setting time and stability effectively. It's versatile. It works well for processes with significant dead time. And for the last one is that is adjustable that can provide an aggressive or conservative tuning depending on process needs. As disadvantage, we've got that it requires an FOPDT model, assumes the system can be approximated as a FOPDT, which may not hold for the complex processes. Is as optimal for nonlinear systems. It does not work well with highly nonlinear systems or higher order dynamics. And the last one is that is limited dead time compensation, that it may not perform well for processes with very large dead time. Next one.
Cohen-Coon tuning is a powerful method used in chemical processes to optimize control and enhance efficiency. In reactor control, it helps maintain the right temperature, pressure, and reactor concentration, preventing side reactions and runaway conditions. For distillation columns, it stabilizes temperature profiles, condenser. In heat exchangers, it adjusts parameters to account for fouling, ensuring efficiency, and improving heat integration in chemical plants. Multi-variable process units, like cracking units, benefit by optimizing yields of valuable products, while polymerization reactors see better control of molecular weights and production rates. In wastewater treatment, it enables biological processes, improves effluent quality, and boosts energy efficiency. Finally, for gas processing, it plays a crucial role in gas sweetening and liquefaction processes.
Let's start with this scenario. We'll develop appropriate PI tuning parameters for a temperature control loop on a heat exchanger that uses cooling water to cool a process fluid. The controller is set on manual and the controller output is decreased from 57% to 54% instantaneously. The change in the process fluid temperature as a function of the time is provided. Based on this information, use the Cohen-Coon tuning methodology to determine the values of the parameter on the for a PI control. Our goal here is to take this data and determine tuning parameters for a PI control using the Cohen-Coon methodology. First of all, we must know that this is an open-loop testing, which means that it involves placing the controller in manual mode and adjusting its output directly. The adjustment impacts the valve, which in turn affects the process. However, it's important to know that whether the valve opens or closes as a result of the adjustment depends on whether it's configured to fail open or fail closed. The primary purpose of the open loop open-loop testing is to derive a transfer function that represents the combined behavior of the valve, sensor, and process. For the Cohen method, this transfer function must take the form of the first-order plus dead time FOPDT model. The step input in the test data allows us to what is called process reaction curve method or the step test method. To find the FOPDT parameters, we follow these steps. First, we identify the inflection point in the process curve, which is shown as the star. Next, we draw a target line for the inflection point. Now, we use this line to determine where the curve process the initial and final value from the process output. From this data, the dead time, or theta, is found to be 5 minutes, as it corresponds to the time in which the process crosses its initial value. The time constant, also known as tau, is found to be 4 minutes, calculated as the value shown as 9 minus the theta or lag, which equals now to 4. Also, we also notice that the temperature decreases from 55 degrees to 53.2 degrees. Once we have all this data, we will be able to find our first order plus dead time FOPDT model, which is mathematically expressed as the equation on the left. With theta and tau already found, now we have to find the gain, which is calculated by the change in the output variable, such as the decrease of temperature from 55 to 53.8 degrees, and the change in the controller shown in the statement, which goes from 57 to 54%. Once we have this, which now equals to 0.6. Once we have the transfer function, we are now able to get the PID parameters from the Cohen method for a PI control. We use this chart above, which is especially for this Cohen method. And once we replace all our data and we choose the right model and the right equation, we can get the KC and KA parameters, which is approximately 1.34% controller output per percent transmitter output, and tau, the integral time, is about 4.96 minutes. That's all. Thank you so much.